This is the second part of the video clip for Lecture 6. On this and next slides, I am going to give you a quick overview to talk about all metering infrastructure before I get into Michigan Tech metering infrastructure deployment project. And from this part of this video clip, you will get the intuition about how this multi-stage deployment will benefit the better study of the load profile at Michigan Tech. Recall what we have discussed earlier about the diversified demand and non-coincidental demand. As you can see from this picture, the diversified demand, which is shown at the root node of this case, and the non-coincidental demand, which is the D sub I, shown at each of this child node. And sometimes, as I said before, it could be between the substation feeder head and each of the FRTU, or a distribution transformer load survey correspond to each of the individual household. In this case, as you can see that the curve for each individual household can be very different from time to time. And as I mentioned earlier, the tricky part of it is to gather all the data set from each household, and right now up to this stage we do not have the metering infrastructure for each of them. So what we have to do is to do the load survey to get the snapshots of data from each household, and then we lump it up together for each of the distribution transformer, or it could be the same thing for each of the substation feeder head correspond to each of the FRTU. So this is the kind of study that we have been doing a lot. And fortunately, that if we do it right to strategically deploy all this IP-based metering infrastructure across primary and secondary part of the distribution network, we can pretty much obtain the kind of the data that we need to find out. So this is another summary that I'm showing you here, is that will give you a bigger perspective from feeder head the RTU, the remote terminal unit at the substation level, to the overhead line, which is the feeder remote terminal unit. All of these are under the primary network of the distribution system. Now, sometime after this distribution transformer, which became the secondary part of the distribution system, we are going to having more smart meter deployed at each child node. In this case is the customer. So as you can see that this is operating in radio network topology fashion, and then the unidirectional flow of power from substation is what is shown here. And this is the unbalanced three-phase analysis, because we have tapped on different phase of the distribution transformer over the lateral or different feeder that result in unbalanced situation. So the method to allocate load is pretty much have 4 different ways summarized here. So application of diversity factors play a crucial role. So if you have a good diversity factors, you can use this number to find out how we can allocate a good number for each load. Because ideally, as I said before, if a feeder consists of 1,000 customers, we would like to have all of them deployed with a smart meter. But 1,000 smart meter will cost more to utility, and as a result, it become a economic issue. So sometimes it will make sense to have a balance between some part of the network have high fluctuation of load, and some location is not as that fluctuating thing. So this feeder maximum demand actually will be also useful to find out the maximum and average value, as I mentioned earlier, which was sort of the way how we can derive loss factor for each feeder. So these are the methods that to allocate loads that utility crew has been using those methods to find out the best way to model each individual load for each feeder. So what I am going to start discussing about what we did here at Michigan Tech is we did the same thing, is to find out the number of buildings across campus, and then we do this evaluation based on the historical trend that we have over the past decade. And I think we were very fortunate to work with the facility folks that to get the data from, because it sounds to me that this is a win-win. And one way is what we do is to find out the consumption of each building throughout the year, and then decide the deciding factor would be to figure out which building is worthwhile to put this IP-based meter out there. And so what we did was we get all this data for each building, consumption data, and then we sort it out in the descending order, and then we'll say, okay, we have this much of budget, why don't we just put this on those high consumption building. Sometimes high consumption doesn't mean the high fluctuation, but the high consumption of each building will have a strong influence per feeder loading condition. So if you know the current consumption at any time from the meter, that will actually help to better predict the smaller number for the rest of the feeder. That was the strategy we did. And as you can see from this picture, what we did was the ERC building, which is what most of the electrical and computer engineering faculty and classroom in this building. So we have usually have two circuits. So sometimes, so what you see here, this is the circuit is always closed. This is the circuit is always open. It's like a tight switch, but it's not quite the same way how we do it in residential area. But this is actually will improve the reliability. Let's say if feeder 2 is completely de-energized. So this is a one-line diagram. So you know that it consists of three-phase feeder 2. So feeder 1 and feeder 2 and feeder 3 will give you the perspective that in case feeder 2 is de-energized because of a faulted situation, then we can energize this building from feeder 3. Bear in mind that all this distribution lines are buried under. So we have it's not like the reliability of the overhead line can be more vulnerable because of the exposure to the weather related problem. So, but still, this is the kind of information we have for Michigan Tech. So the definition of how we do the coverage percentage for each building is we have an injection point at substation of distribution network, right? This is a meter at the feeder head, and then we have each smart meter for selective numbers of buildings. So in this case, if we have 11 buildings have AMI, then this meter will be used to decide how much the percentage of the coverage. So this is a measure that say we have 11 buildings, we sum out all the building metering data divided by the total consumption from the all campus. So as I mentioned, we have 3 major feeder for each for Michigan Tech campus, so we can just sum it out and see what is the total coverage for based on those 11 buildings. So the total coverage may not be always the same because some building may nominate a value, some building may not, depending on the season and depending on the activity throughout the year. So it could be very different from season to season. So to give you a perspective, this is the kind of data we shown. We get it from certain part of the year, and if I may just zoom in a little bit, let's see. So this is from 2012, from July to December, and this is, as you can see, this is the total. This is a histogram that we have it from that 6 months in 2012. And those data, as you can see, this is the average value, which is close to 4,500 kilowatt, and then the maximum sometimes can be up to about 7 megawatt. So it really depends about the season. So you can see that sometimes we don't have enough data. So that's why the frequency is less. But this doesn't mean that is inaccurate. So this is the kind of snapshot we have from those 11 buildings. And then this is the percentage between the injection and the telemetered load. So we're talking about the ratio between the 11 buildings as well as the substation's feeder head meters. So it changed really from maximum 65% all the way to 42% mean value. So the coverage is pretty much around 40%. As you can see, this is the peak of the histogram. It's pretty consistent here. Throughout this 6 months, July, August, September, October, November, and December, the coverage is pretty consistent. So this will be very useful information for us to decide what would be the next step for us to deploy more data, metering data. As you know, all of this will cost not just the initial capital, but as well as the maintenance cost. For example, you will have to actually work with the facility folks to actually find out with the contract how we can pay the IT department each month the service that we use from acquiring the IP data set from the meter all the way to the center, the facility center. So you will get a chance to ask a lot of intelligent questions when you visit there sometime in February. So this is something will be helpful for you to learn about the load characteristic. This is a better picture to show the statistic of the existing power distribution grid at Michigan Tech. So as you can see, we have approximately 38 buildings. Not all the building is heavy loaded, so we actually pick the 11 building, which could be sum up more than 50% of the consumption campus-wide. So as you can see that the rest of the 28 building is not really a heavy load building. So just to give you an idea about how we actually begin putting all this deployment in the first place. And we have 3 feeder, 1 injection from UPCO. This is a point of coupling. And then we have 4 generating unit in parallel with the substation. So in case of there's a blackout in this area, Michigan Tech campus will still have power. Why? Because we have 4 generating units that will be able to serve throughout the entire grid. Not to say that there are some building that is connected with some backup generator that's for emergency purpose. For example, to make sure that the elevator is turned on all the time, and this will help when during the emergency situation, people will not be stuck in elevators. So these are the existing metering technology that we have deployed at Michigan Tech. As you know, that some of those can be the old-fashioned how we can get data, but this is not IP-based communication. So the facility crew will have to go to the site to get the data once or twice every month to keep up to date about what is the consumption of each building. And we have done something very interesting at campus in terms of getting all those data. One way is to deploy a obsolete gadget like smartphone, older generation, to put somewhere there to snapshot of this and then convert this data into the ASCII information, and that way will help us to save some cost to those smaller consumption building instead of spending thousands of dollars to replace completely with the IP-based solution. So this is one of the alternatives that we have been doing. And then we also have the frequency disturbance recorder. So this is a one-phase PMU, phasor measurement unit, if you had heard about that. And what we do here is to put this FDR unit across 3 different feeders to sense the frequency information. This is just a load profile that how we get it for every 15 minutes from a dormitory, the building 38/40 McNeil. So as you can tell that this distribution transformer for McNeil, so this is one distribution transformer, the second one, and this is spring semester. So right, so spring semester and summer, nobody lived there, so the load is abruptly changed it to less consumption, and then as we are going to begin fall semester, this number got ran up, and as you can see, it fluctuates from time to time, depending of the time of the day, and the same thing for second feeder as well. So this is the green part, and this is when that's the summertime before the commencement. I think I highlight at a different date. The September the 4 Tuesdays is when the fall semester 2012 semester begins. So this is the frequency disturbance record data. As I mentioned earlier, we actually did put at 3 different feeders, and we start working with the University of Tennessee Knoxville. What we do is that the good part of this device is that it's something like a home appliance. We can actually move this easily around the campus so long as we have an outlet that can plug in to measure power, and then at the same time to have a good reception to get the GPS data from the satellite. And the reason we need satellite for the PMU kind of thing is to synchronize with the time, not to get the precision, to synchronize the time across different devices in the network. If you go to if you type in University of Tennessee Knoxville and FDR, you can see live information from the FDR system from across the country. That's pretty amazing how they get the data and synchronize them. In case of a disturbance, they should be able to get use of this data to do some sort of analysis. So this is the picture I'm showing here. This is I think this is in the reverse order, but that's fine. We can rotate that later on. The one thing is the frequency information. As you can see, that this is all the FDR device from the rest of the country. Eastern, to be precise, is Eastern interconnection. And then the blue part is actually showing very, very different from the rest of this. This is what we call not coherent, which means that something could happen is an islanding. And this is the data, but we get it from the same thing for the angle information. It's sort of deviate from the rest of the system. So when I taught the 6210, the power system dynamic and stability, we sort of addressed this issue in the first day of class, because we thought that instead of going through this modeling, we can actually see the real life event and how we relate frequency and angle information from the instrument. So to simply put, what's happening here? What happened is Michigan Tech actually have a drill to disconnect the entire grid of to disconnect Michigan Tech distribution grid from the rest of the interconnection. And we have that for generating unit use it here, so we can use that to serve the grid without having any power outage. But as you can tell from this curve is that we are actually sort of independent. We form our own island in this case. So for the rest of the information, just to show you what local generating unit would be. So the blue part circle outline is actually those buildings that have a backup local generating unit. It can range from 125 kVA to 569 kVA, and the total rating of all this generating could be about 2.3 mega MVA. So as you can tell, it's probably half of the entire grid consumption for another backup. So we have backup at the substation level. We also have the backup for each building, and then we also have a redundancy between two feeders. One is a primary, one is a backup, and that one backup we usually refer as a tight switch or normally open switch. So we have 3 redundancy in Michigan Tech system, not to mention that we have underground system. So we probably have one of the most reliable system in the UP. And The rest of it is just to show you the cluster, how we actually do some sort of study that if you want to make that cluster in the future, how we can group them together. These are the possibilities. This is a picture to show you that the substation, how we're going to talk about that next in terms of planning. And this is Michigan Tech population, Houghton population, Hancock population. So you know that in case that if you want to work with a utility in distribution system, you might have to learn, if you're going to build a brand new sub-distribution feeder toward this direction, what kind of model you will be using, which will lead us to the next chapter, chapter 3. And in this picture, it's just simply to show you that we can actually share the system responsibility by export-import power between different parts of the area. Let's say from area C to area B, or vice versa. Same thing to the area A. But then we don't have a distribution system that actually connect directly across the river, the lake, to the other part of the area. So the only thing that we have power going to the area A is through transmission system. So those are the possibility in distribution planning, that how we are going to do the sort of study in terms of without compromising the power loss, as well as the maintaining a good voltage profile for each feeder. This is a sort of study that we will have to go through. And with that, this concludes the lecture of today's lectures.